All right, so here we have a problem dealing with a magnetic field, right, drawn in blue, and a moving proton. Right, we know its initial velocity and both magnitude and direction, and we want to figure out some stuff about it from that. So, first step, calculate the magnetic force initially on the proton. So, we know an equation for the magnetic force, Q V B. And normally we stop there because in a lot of problems, the motion is perpendicular to the field. V and B are perpendicular. Here they're not, so we can't forget there's a sine theta term dealing with the angle between those two things. And so that's what we need to figure out how to sort of substitute numbers into. Right? We're given the value of B, we're given V naught, we know the charge of a proton from our equation sheet, and so we just need to figure out how we do this angle part. So the first thing, we were given an angle of 30 degrees. But, right, if I take this V naught vector and kind of redraw it, right, like this, right, is B, and that's V naught. 30 degrees is not the angle between those two things. The angle between those two things is actually this one that I've drawn in green, which, if this is 30 degrees, this is 60 degrees. And so what we need to use for theta is that, right? Theta always represents the angle between the field and the velocity. 30 degrees is not that. We had to do some geometry to find it. That's the first step. Now we can just start plugging in. So, charge of a proton, 1.6 times 10 to the negative 19th coulombs. Right, we have to work in coulombs. V naught, we're given, is 4 times 10 to the 7th meters per second. B, 1.2 Teslas, and then the sine of 60 degrees. And so at this point, now you've got everything looked up, you plug it into your calculator. Right? Don't try to do it in your head. So 6.65 times 10 to the negative 12th newtons is what you get if you do that very carefully. Right? Be careful with the scientific notation, but since there's no division, it shouldn't be too bad. So that's the magnitude. The next step is to figure out the direction, and that means right-hand rule. So our thumb points in the direction of V naught. We know it's a positive charge because it's a proton, so up and to the right. B is down to the bottom of the page. And it doesn't actually matter that our proton is traveling at an angle up and to the right or just to the right. Either way would be the same, or you can kind of see that your thumb, as it wiggles around, won't actually change the direction of your index finger, which is the force. And so no matter what you do with your thumb's direction, your index finger is going to point down into the page. So that would be part B. Right? And it doesn't ask for an explanation, so you don't have to write any of that, but again, if you did, it'd be using the right-hand rule. You'd explain the three pieces, right? The direction of the velocity, the direction of the magnetic field, and therefore the direction of the force. Okay, so that's parts A and B. Part C, how much work will the magnetic field do? Well, work is, in general, FD cosine theta. Right? So the force, since we can care about the magnetic force, this is the magnetic force, FB. D is sort of the little bit of distance that it travels. And this is a little bit tricky because we have to think carefully about how this proton moves. Right? What's given is V naught, but it doesn't travel in a straight line for a while and then do something. Right? It doesn't do that. That's wrong. What it does, really, is follow, I'm going to change colors to kind of an orange-yellow, I think. Yeah. So what it really does, right, the V naught is only describing the velocity direction at that instant split second, but we know that it's going to go in a circle, right? And if we just let it sit there, it'll go in a perfect circle and get right back where it was. right? So it looks like there's a sort of a good straight distance that's traveled, but there never really is. It's always curving. And so if we follow the right-hand rule, we find that, right, D, this is really, let me go back to red. Oops. So right, this D is really saying the direction of, this is like the direction of the velocity, the direction it's moving in. That's really, because we don't need to, as you'll see, we don't need the number. That direction of the velocity is, the direction of the displacement that's traveling is the direction of the velocity, because it's always turning. And now we have to think, go back to this calculation down here, right? What do we know about the magnetic force and the velocity? Well, the magnetic force is into the page. The velocity is in the plane of the page, right? Those are always perpendicular. So what's theta? Because those are always perpendicular, this is always 90 degrees as it goes in the circle. No matter what, right? The magnetic force is always into the page at every location around this circle. They're always perpendicular. So, cosine of 90 degrees, that's one you should know. So this is FB times D times 0. And so it doesn't matter that this would be a very, very complicated calculation because the direction it's moving in changes and it's a circular path and all. It doesn't matter because it's perpendicular. And so the answer is 0, and you have to remember the units, right? Work is an energy, it has units of joules because it relates to energy. So 0 joules. And this is pretty typical of most magnetic field work problems. It's a really common trap. You have to be very careful when you see magnetic fields in work because it's almost always going to be 0 joules. And in doing part C, we've actually already kind of done part D, right? It says describe but do not calculate the path of the proton in the field. Well, that's that orange, right? That's this what I drew right there, right? That's how we knew, in some sense, there was 0 work. We had to describe that it moves in a circle in that plane. So I would describe it as it moves in circles, and since our coordinate system in the original problem, the plane of the page is labeled as the XY plane, it moves in circles in the XY plane, always perpendicular to the force. It's moving at a constant speed. I think actually I misspoke. Sorry, I drew my circle the wrong way, mainly because I can't draw in 3D. This circle should actually be drawn sort of up and down, which again is, it's like if I was going to, I'm going to go another page. So if the magnetic field is coming out at you like this, I've rotated the image by a lot. So now V naught is kind of going like this. The circle is actually going down and around this way. So in the coordinate system we're given, this is the Z direction, this is the X direction, and then back on this one, this is the Y direction, this is the X direction. So I got my pictures a little bit messed up because 3D is tricky. But so the right answer is that it makes circles in the XZ plane, and it is at a constant Y position. And the other part that's useful to remember is the direction that it's moving in. Which, again, if I add these arrows on here, right, it moves clockwise at a constant speed, right? We know it's a constant speed because magnetic fields don't do any work, right? If it did work, we have to speed up or slow down. So a lot of details. It's very tricky to draw and explain these 3D ones carefully, so make sure you think sort of as clearly as possible before you start putting it on the page.